Good morning. In today's session, we are supposed to study about the EMF equation of the DC machine. In previous session, we have studied about the construction of DC machine. We can say DC machine as an electromechanical converter because we can use DC machine to convert electrical energy into a mechanical or vice versa. It means what? We can convert mechanical energy into a electrical. Then we have seen we can use the DC machine as a DC motor or the DC generator. If we are using the EMF, it means what? Electrical energy. At that time, we can say that type of machine as a DC motor. And if we are generating the EMF, just wait for a minute. Message. Suchita, is there any issue? Why you have written there? Don't know. Okay. What up we are saying here? After that, we have seen the construction of the DC machine. So the construction for the DC motor and DC generator both are having theoretically same constructions. DC machine consists of the main two parts. These are nothing but stationary part and the rotationary part. In stationary part, stator consists of the main poles which are used to generate the magnetic flux. Again, commutating poles that are between the main pole to avoid the sparking in the commutator. These are the stationary part in the DC machine. Then we have seen about the rotationary part. If you see the construction for the DC machine, at that time you will get rotor will consist of the armature of the metallic body, or we can make the rotor by using the cover with the slots to get the air gap. Again, if you see the construction for the DC machine, at that time you will get armature conductor, commutator. These are the rotationary part of the DC machine. Now we are supposed to study about the EMF equation of the DC machine. So here what we are saying about the DC machine, here when we are supposed to give the power supply to the DC machine, at that time if that type of machine is using the electrical energy and it will convert the electrical energy into the mechanical energy, at that time we are saying that type as a DC motor. And if it is doing exactly vice versa with this, we are saying that type of machine as a DC generator. But when we have seen the construction at that time, what we are seeing, all these things are depending on the rotationary and the stationary part of the DC machine. So these things are depend on how much current will flow, how that current will flow, and how there will be the rotation. So here we can calculate the EMF equations that will be generating in the DC generator, or that EMF which is we are calling as the back EMF that will be introduced but in the DC motor. And we are saying that EMF as a back EMF because in DC motor we are using the energy, electrical energy, and we will get the energy at the output that will be mechanical. And that EMF we are saying as the back EMF because that EMF is working in the opposite direction with respect to the supply voltage. That's why we are calling that EMF as a back EMF in the DC motor. But in DC generator, we can say that EMF as a generated EMF. So we can call that EMF as a E suffix G. And in DC motor, we can call that EMF back EMF E suffix B. So here, when we are supposed to find the equation, derive the equation for the DC machine, at that time, we can say P as the number of poles of the machine. Number of poles means what? When we are using the machine, at that time, we are using the pole as a conductor. On that, we are putting the winding, pole core, field winding. This is nothing but we are making the field winding to get the magnetic field. And when there will be the magnetic field, it will cut by the conductor. According to Faraday's law, EMF will get introduced because magnetic field वहां पे generate हो रहा है. मतलब क्या हो रहा है? Magnetic fluxes generate होंगे. So here we can say phi as a flux per pole in the Weber. Z is nothing but the total number of armature conductor and speed that will be measured in the rotation per minute. And if we are calling that capital N ki jagah small n, that time that will be the speed of armature, but that speed will be measured in the rotation per second. ये जो स्पीड है कैपिटल एन वी आर कैलकुलेटिंग इन द रोटेशन पर मिनट आरपीएम, स्मॉल एन आरपीएस रोटेशन पर सेकेंड. A is nothing but the number of parallel paths in the armature winding, because when we have seen the construction at that time we are saying armature conductor are connecting in the series but making these parallel paths to get the EMF to generate the magnetic flux. So here in one revolution of the armature, when we will give the power supply at that time, armature winding will start to rotate, and in one revolution flux cut by conductor, because according to the Faraday's law, when flux will cut, when magnetic field will cut by the conductor, flux will generate. So we can calculate this flux for one conductor, that will be P into phi, number of pole for that conductor into the flux. So you will get the flux cut by that one conductor. Now, when we are supposed to calculate the time to complete the one revolution, what we are saying? We are saying that speed is in the rotation per minute. So for capital N, that revolutions will take the time that will be in the second. So here we can take T equal to 60 by N, because we are considering one revolutions equal to T, and we are aware about the minute and second conversion. We are taking speed in the rotation per minute, but we will require the time that will be in the second. So here 1 minute को मैं करूँगी 60 seconds में conversion. तो 1 by n को क्या हो जाएगा? 1 into 60. 1 minute equal to 60 seconds. 60 by n. So you will get time that will be the reciprocal of the speed. So you will get 60 by n in the second. N is nothing but I have given here. N is speed and T is the time. The time required to complete the one revolution. To complete one revolution. So here, now we are supposed to derive the EMF equation. So here we are supposed to derive EMF, that will be the average induced EMF in one conductor. So you will get E equal to P phi upon T, because this is nothing but the number of when we have seen the flux cut by one conductor. That is nothing but P phi. So you will get the P phi with respect to time, that is nothing but P phi upon T, but we are taking the time, that is nothing but 60 by n. So you can write E equal to n P phi upon 60 volts, because EMF is nothing but the voltage. But if that EMF is introduced in one conductor, we are supposed to find the average induced EMF that will be across each parallel path for the DC machine. So if we will require number of poles, at that time we can calculate E equal to NP phi upon 60 into Z by A. Z is nothing but we can take Z as the total number of conductors, and number of parallel path in the armature winding we can call as the A. So you will get the cross sectional area for whole parallel path for that conductor. So you will get Z by A. So you can calculate E equal to NP phi upon 60 into Z by A. That will be the average induced EMF for each parallel path. So you will get E equal to NP phi upon 60 into Z by A. So here we are saying that EMF that will be in the DC machine. Now we are supposed to study about the EMF that will be for generated, and that EMF which we are calling as the back EMF in the DC machine. because that EMF will work in opposite direction with respect to the supply voltage. Suchita, are you facing any issue? You have raised your hand.
Sorry, ma'am. Sorry.
Okay,
It's
by
by
mistake.
mistake.
Okay, it's fine. So here, what we are saying here, if we are using the DC machine at that time, if that DC machine is generating the EMF, it is using the mechanical energy and it is generating the EMF, that EMF will call as the generated EMF, and that EMF will get the equation like NV5 upon 60 into Z by A. There will be question numericals on the EMF. So you all are supposed to understand this equation, because this equation will be needed in whole this unit. This unit is very lengthy. This is the theoretical, but there are some numericals. These are very much easy, but theory is bit complicated, because there are the lots of things you are supposed to study. You are supposed to study about speed characteristics, torque characteristics. You are supposed to study about the different types of the DC machine, shunt DC machine, self-excited, shunt, separately excited DC machines. You are supposed to study about the sorry, the different loads which we are connecting at the output of DC machine, which will rotate with respect to the DC machine. These loads which we can at the domestic level, which we can use at the industrial level, agricultural. So you are supposed to understand that equation. After that you will get how we will calculate the torque. After that you will get how we are using the KVL in the separately excited and the shunt excited DC motor. So you are supposed to understand these equations. If you are not getting any point, you can unmute and you can ask me. Okay, so what we are saying, if we are using the DC machine as the DC motor at that time, that induced EMF we are saying as the back EMF, because that EMF will operate in opposite phase with respect to the supply voltage. What we are saying about the DC motor, हम जब उसको power supply दे रहे हैं, at that time it will uses the electrical energy and it will give us mechanical, but there also we are using the field winding, so it will generate the flux, due to which EMF will get introduced, but that EMF will work in the opposite direction with respect to the supply voltage. That's why we are calling that EMF as the back EMF. Equation will be same, only that EMF will operate in opposite direction. So we can see that EMF as the EB. So here we are supposed to see what is the need of that back EMF. So here, when we are using the DC machine at that time, what we are saying according to the Faraday's law, according to the electromagnetic induction phenomenon. This is nothing but this is the Faraday's first law. What we are saying, when conductor will cut the magnetic field, at that time EMF will introduce in the conductor according to the electromagnetic induction phenomenon, or we can say according to the Faraday's law. So here we are supposed to study about the Fleming right hand rule to decide the direction of induced EMF. So here, what Fleming right hand rule states, that it is seen that direction of induced EMF is opposite to the applied voltage. When we are giving the voltage to the DC motor, at that time EMF will get introduced, but that EMF will work in opposite direction with respect to the given voltage. So we can say that voltage as the counter EMF or the back EMF. So Fleming right hand rule, again we will see these things we will require, but here firstly we will see why we will require the back EMF. What is the need, what is the significance of back EMF, and which EMF we are saying as the back EMF. So understand these things here. So what we are saying here, we are saying that EMF will work in opposite direction. With respect to whom? With respect to the given voltage. So we are saying that EMF as the back EMF. But that EMF is developed in series with the voltage, but only it is having different directions. So here that EMF will causes the current which will causes it. it will opposes that current. That's why we are calling that EMF as the back EMF. But what is the need of that EMF? Significance. If you see, if there is no EMF, what will happen? If motor will start to rotate, at that time, higher amount of power will dissipate. And therefore, that power will wasted and there will be no power will remain to do mechanical work. That's why there is a need of back EMF. There will be question what is the need of back EMF in the DC machine. At that time, you are supposed to understand back EMF will be needed in the DC motor, not in DC generator. Because DC जनरेटर में तो EMF जनरेट हो ही रहा है, but in DC motor we are saying that EMF as back EMF because it is operating in the opposite direction with respect to the given voltage. So here we can say back EMF which will represent the portion of supplied voltage which multiplied the current equals the mechanical work. At that time where we will give the voltage, at that time the rest of voltage will be used as a IR drop and it will produces the heat because that motor will start to rotate. It will reduces the heat. So we will require the EMF that will be close to the supply voltage because we are wasting the given voltage to produce the heat to get the power dissipation. So here we are supposed to use the back EMF which will play as a self-regulating role, which will give the power to do mechanical work and which will allow to energy flow through the motor. So in a parallel motor, it is only due to the back EMF. Parallel means DC shunt motor. DC shunt motor. So it is only because of the back EMF if we are giving the voltage source that will be equal to given voltage at that time. That if you apply voltage source to the armature with the very low resistance, if there is no load or the full load, that motor will run nicely because of that back EMF. Because that EMF will be in proportion or close to the supply voltage and it will give us energy to do the mechanical work if there is no load or the full load. At that time also that motor will run very nicely. So here we are supposed to study about the significance of back EMF in the DC motor by using the circuit diagram. So this is the circuit diagram for the DC motor. This is the DC motor. These are the brushes. This is the shaft. After that, we are giving at the output load. Any type of load you can connect here. So here, when we are giving the supply, at that time there will be some amount of resistance across the armature winding. So we can call this resistance as a armature resistance RA. We can call EMF that is produced across DC motor as EB. We can take EB. We can call the current flowing through this motor as a armature current. And we can call this DC motor as a armature. तुम यहाँ पे सिर्फ DC motor के जगह armature conductor or armature you can write because armature is the heart of DC motor. If we are supposed to take field winding, you are supposed to write the name. But rotor is the heart because at that time only that motor will start to do work. So here when we are supposed to understand the significance of the back EMF, at that time you are supposed to study about the circuit diagram of the DC motor. That will be the series DC motor because here we are connecting resistance in series with the DC motor. So here we can take one example like we are taking the DC motor with the supply voltage 12 volt. If we are giving here E equal to 12 volt. At that time, if armature resistance is 0.1 ohm, according to the Ohm's law, we are aware I equal to V by R. Here we are calling supply voltage as E. So E by R. E 12 hai, resistance 0.1 hai, you will get value of current flowing through the armature. And this resistance is in series with DC motor. So the same current will flow through this DC motor. Now you are supposed to calculate the power. How will you calculate V into R? V का वैल्यू कितना दिया है 12 ohm. I का value we have just calculated 120 ampere. So you will get the power that will be 1440 watt. W is nothing but watt. So here, when we are giving the power supply to the DC motor, at that time it will reduces that power that will be lost in the form of heat. So here there will be no power left to do any mechanical work. That's why we will be needed the back EMF, because यो जितना power हम generate हो रहा है, when we will give the power supply, तो क्या हो रहा है, all that power will goes to heating. All that power we are wasting in the form of power dissipation. It will generate the heat, and there will be no power left to do mechanical work. That's why there is a need of the back EMF. Who has joined the class? 6 people. Priyanka, Nishigandha, you guys are supposed to join the class on time. Okay. Now, if we are applying here KVL to this circuit, we are aware about KVL. What we can do here when we are applying the KVL? Algebraic summation of the potential drop for each and every component across loop will be equal to 0, or you can take potential rise equal to potential drop. So if we are taking potential rise E equal to, yeah, if we are saying here RA resistance, and we are calling the current flowing through this as a IA, you can take that resistance as a EMF as a IA into RA. So you can take IA into RA. We are aware about the DC motor. DC motor, what we are saying? We are saying there is a EMF produced. That EMF we are calling as the back EMF. So we can take EB plus IA RA. So you will get E equal to EB plus IA RA. EB means यहाँ पे जो जनरेट हो रहा है, और ये RA का वहाँ का EMF RA into RE. So you will get this. So here what we are saying, if we are not generating the back EMF at that time, when we are giving the power supply, all the power will lost in the power dissipation and it will generate the heat. So here, if we are taking the resistance drop across the armature RA, that will be negligible. So you will get E equal to EB. But what will happen here, that EMF will operate exactly in opposite phase. ये E positive है तो ये negative रहेगा, ये negative है तो ये positive रहेगा. But both are having approximate the same value. So here, if we are giving the supply voltage 12 volt across the armature, it will split internally as a sum of two drops. That is nothing but some drop will go to this resistance and some will drop to this DC motor. We can say that as a EMF, back EMF drop. And here we can say IR drop, the voltage drop. So here we can say the value of back EMF will equal to the supply voltage when we are ignoring the resistance, that will be the of armature value. So here, what we are saying, if we are taking E equal to EB, practically what will happen, when motor will start to, when we will give the power supply, motor will start. And if armature is not moving, again what will happen, EB will become equal to 0. EB will become equal to 0. So this is in the practice term, if back EMF will equal to the supply voltage and it will leaving only the small fraction of the supply voltage, at that time there will be no back EMF, EB equal to 0. And if the value of armature current is high, only limited by the supply small resistance of the armature, so you will get initial torque that will be very high. So here what we are saying, we will get the value of E equal to EB plus IA RA. ये जो हमने पहले इक्वेशन लिखा था. How we are writing when we are applying KVL to this circuit? We will get this equation. So here we can reconvert that equation in the form of EB. Rearrange that equation. So you will get EB equal to E minus IARA. These equations you will be needed to solve numericals. This is also E equal to NP5 upon 60 into Z by A. This equation. After that, EB equal to E minus IARA. These equations you will be needed to solve the numericals. So what we are saying, as the back EMF will grow, it will increase. Current drop and the torque will reduces. It all settles at the point and torque will become equal to the load. So here for reasonable load and the small armature resistance, the back EMF will be required, that will be equal to the supply voltage. So here we can see we will require E equal to EB, because if there is no EB, what will happen? That armature will not move. So for the reasonable load and the small armature resistance, we will require the back EMF that will be equal to the supply voltage. And here we are supposed to study about the torque. So what we are saying here, torque is nothing but it is the measure of the tendency of a force that will cause to a rotational motion. It is nothing but it is the moment of force that will produces rotational motion. It is means you can take that as a F into R into sine theta, because we can say torque as it is defined as it is the product of force acting on a body and perpendicular distance of a line of action of the force. मतलब force or distance we are calculating by letter R. This is nothing but the resistance, this is nothing but the radius we can call this is as a perpendicular distance. But when motor will rotate, we can take this as a radius distance. So he can say here torque as it is the product of force and the perpendicular distance of force into that angle. Angle ka sine. What we are saying here, we can calculate torque equal to F into R into sine theta. F is nothing but the force. So what we are saying here, when our DC motor will start to rotate at that time, torque is nothing but it is the tendency of force which will cause to rotate that motor. So we can bring that motor to change the rotation. So here you can calculate the torque as tau equal to F into R into sine theta, and we can denote torque by letter tau. Torque we can denote by letter tau. So here when we are studying about the torque equation at that time, you can see the front view of the DC motor. You will see here conductor will experiences the force and conductor lie near the surface of rotor. We can take that perpendicular distance as a radius from its center. So here we can take torque which is produced at the circumference of the rotor, and rotor will start to rotate. So here when we are supposed to calculate the torque equation at that time, if that DC machine is loaded either as DC motor or the DC generator, rotor conductor will carry the current and we are putting the air gap. So what will happen? This conductor lie in the air gap magnetic field. So here each conductor will experience the force and that conductor will lie near the surface of rotor at the common radius, and we will get the torque that will be around the circumference, and we can calculate that torque which will equal and opposite to the provided prime mover. You can calculate torque equal to F into R into sine theta, and you can call that torque as the electromagnetic torque. So here we are supposed to study about the equations, torque equation. So here we can see when we are applying here KVL, you will get the equations E equal to EB plus IA RE. So what we are saying here, if you are multiplying this equation, equation 2, if we are multiplying both sides of this equation by IA, you will get this equation. If you are multiplying both equations by I, You will get this equation. Now, we are aware about IA square RA. You can take this as a power loss because IA square RA, you are aware about the power equation V into I, or you can write I square R. So you can take IAE plus IAEB plus power loss, because total electrical power is nothing but the mechanical power, and you can take mechanical power equal to IAEB, but we are aware about the mechanical power that will be in the form of angular speed. You will get mechanical power that will be in the form of angular speed, and torque Tm equal to tau into W. W is nothing but angular speed. So you can take that speed in the rotation per second. So you can say 2 pi n into t. N is nothing but rotation per second. So what we are saying here, we are saying mechanical power equal to IAEB. Here, this is the power loss. This is the power loss and this is the mechanical power, which we are giving the input voltage at that time. That's the input power. So EA EB equal to, we can take this power. This is nothing but WT. WT means 2 pi NT. So you can equate these equations. You will get the torque equations. You will be needed these equations to solve the numericals. Tau equal to EBIA upon 2 pi small n. Small n, that speed we are taking in the rotation per second. So here we are having the equation for the back EMF, that is NP phi upon 60 into Z by A. So you can again write the value for EB here. You will get the equations that will be for EB equal to, if you are taking that in the form of second instead of capital N, rotation per minute, second में ले रहे हो, what we can do, we can take that as a n upon 60, n upon 60. So here we can take EB equal to 60 into n, P5 upon 60, because यहाँ पे 60 है और ये n को क्या लिखा है 60 into n. Capital N will be n into 60. So n into 60, P5 60 as it is, Z upon A as it is. So you will get torque equation equal to EB RA upon 2 pi n. If you are writing the value of EB here, you will get this equation. Again, you can solve, you can write 1 upon 2 pi equal to 0.159, or you can write the constant terms. These are nothing but which are not changing. The number of poles, this will not change. These are the stationary. The number of conductor, parallel path, Z upon P, Z upon A, this will not change. So you can take this as a constant term, ZP upon 2 pi A, you can take as a K. So you will get the torque equation equal to, that will only depend on armature current and the flux. These equations also you will be needed to solve numerical and to study about the speed torque characteristics for the DC motor. Okay, so remaining syllabus we will see in the next section. Torque equations we will see again tomorrow. Okay, so here if anyone is facing any issue, you can ask me. Now I am taking your attendance. Torque equation थोड़ा lengthy है, we will see again tomorrow. But EMF equation is very easy. You can see here. We will revise and then we will finish our session. What we are saying about the EMF, when we are using the DC machine as the DC generator, at that time induced EMF we can say as the generated EMF. And when we are using the DC machine, that is nothing but as a DC motor. When we are using the electrical energy and we are generating the mechanical, at that time that EMF, induced EMF, we can say as back EMF, because it will work in the opposite direction with respect to the supply voltage. So here the value of EMF will depend on the rotation, how that motor will rotate, and the number of parallel paths, how we will get the magnetic field, how we will generate the magnetic fields. So here we can consider P equal to number of pole of machine, phi equal to the flux per pole. We can give unit for the flux, that will be Weber. We can calculate the total number of armature conductor. We can denote by letter Z. Speed of armature, that will be measured in rotation per minute. We can denote by letter capital N. Number of parallel paths in the armature winding, we can take by letter A. So here flux cut by one conductor we will get as P phi. We are supposed to calculate the flux by whole conductor, the number of conductors we are having. That will be depend on how much number of conductor we are having. So here, if we are taking the one revolutions at that time, if it is taking time t, you can calculate the time equal to 60 by n, because we are saying time that will be measured in the second, and we are taking n equal to t. But what we are saying, we are supposed to take speed in the rotation per minute. तो 1 minute को हम क्या करेंगे, seconds में convert करेंगे. तो you will get t equal to 60 by n. 1 minute upon n, 1 upon n minute. तो what we can do, 1 minute को हम 60 seconds में convert कर सकते हैं. So you will get 60 by n. So here now we are supposed to find the EMF for one conductor. That will be P phi upon T. But we are aware there are the number of conductors available. These are connected in series and in each parallel path. So you can calculate the average induced EMF across parallel path. That will be N P phi upon 60 into Z by A. So here, if we are using the DC machine as generated EMF, we can take that EMF as the generated EMF. And if we are using the DC machine as DC motor, we can call that induced EMF, which will work in opposite direction with the supply voltage, that will be back EMF. Here we have finished about the EMF equation. Remaining syllabus we will see in the next session. If anyone is facing any issue, you can ask me. Otherwise, you guys can leave now. Thank you. I am concluding our today's session.